All of these spectacular happenings are visible manifestations of its existence. An electrical circuit that links the top of Earth's atmosphere, where charged particles are plentiful, to the Earth hundreds of miles below. Scientists at the University of Colorado, Penn State, and the National Center for Atmospheric Research are working to develop a scientific model of the processes across various spatial and time scales within the global circuit.
So one of the important aspects of this project is that there have been measurements taken about the electrical system for the last, 90 years, since 1930, for nearly a century. But there are no really good established models that allow one to verify the interpretation of those measurements and the physical pathways that lead to those measurements. Some of them have profound implications, but we need models to establish their credibility.
Sprites, elves, and blue jets, all shown on this mural, are collectively called transient luminous events, or TLEs, and are believed to be part of the global electric circuit. Red sprites, first verified in 1989, occur from cloud tops up to 95 kilometers, or approximately 10 to 60 miles, in the atmosphere directly above lightning strike activity occurring below. They last no more than a few milliseconds and can resemble carrot tops, columns, or jellyfish in shape. Elves are large, expanding, donut-shaped luminous events, up to 190 miles or 300 kilometers across, that occur for only 1,000th of a second. They too occur over lightning activity, but are believed to result when an energetic electromagnetic pulse propagates from lightning into an area of the atmosphere called the ionosphere. It's brimming with electrically charged particles and at times auroras. It extends from about 35 to more than 1,000 miles in the upper atmosphere. Lastly, blue jets emerge from the top of thunderclouds, then fan out and disappear after about 1/10 of a second, at heights of approximately 40 to 50 kilometers or 20 to 30 miles. They are the only transient luminous event not directly associated with cloud-to-ground lightning. They were first documented in 1994. We have a lot more to learn about transient luminous events and their role in the global electric circuit. For that matter, we have a lot more to learn about the circuit's many contributors, from clouds to atmospheric particles and more.
When we talk about the global electric circuit, we are describing how electricity naturally flows throughout Earth's atmosphere. It can be generated by the interaction of solar wind with Earth's magnetic field, down to the electricity that individual clouds produce. Clouds that produce lightning in a thunderstorm, for instance, feed electricity into the global circuit also. They're all a part of the same system. While we have known for a while that electricity exists in the atmosphere, scientists are just beginning to understand the relationships between the different events that affect it. Could the amount of electricity in the atmosphere change the way clouds and storms develop? Could cosmic rays impact atmospheric electricity and the severity of winter storms? Trying to create a model for the global electric circuit presents incredible challenges. First of all, studying the global electric circuit requires experts across many areas. Scientists who specialize in the uppermost atmosphere, solar wind, electromagnetism, chemistry, the physics of lightning, cloud formation, volcanic weather, and more. Secondly, the model is trying to encompass events that are a part of the global electric circuit on vastly different time and spatial scales, from sprites that appear for a few milliseconds to the 11-year solar cycle, or enormous events like gamma ray bursts down to small particles that influence cloud formation and cloud electrification. And there's even uncertainties about how clouds are charged and how atmospheric conductivity occurs and breaks down. Scientists and mathematicians are trying to create a model that is flexible enough to handle all of those variables. It's a challenge, but there is no time like the present to seek answers to scientific frontiers.
To understand electricity, you really have to understand what atoms are made out of. So they consist of a nucleus that has a neutral charge and positively charged particles. And around that nucleus, you have electrons, negatively charged particles that are orbiting around it. Now, if you are rubbing, for example, like when you're rubbing your hands, you are giving these electrons that are going around the nucleus of an atom energy to leave its orbit. You take him out of that structure and make them mobile. And it's really the flow of these electrons that produce electricity.
So the atmosphere is largely neutral. So you need some energy somehow to break the electrons and away from the neutral atom or molecule. And the way the ionosphere is formed is largely through the extreme ultraviolet radiation coming from the sun. That provides the energy by which you can separate electrons from the atom, and they become free electrons. That atom now becomes positively charged, which is an ion, and that makes up the charged part of the ionosphere, largely from the solar extreme ultraviolet radiation. As we get deeper into the atmosphere, that radiation, it gets absorbed by the upper part of the atmosphere and doesn't reach the surface. You need more energetic particles to further ionize the atmosphere as you get closer to the surface. That's partly brought on by galactic cosmic rays. They have very high energies that can get through the atmosphere, and in that path have a lot of energy, collide with neutral particles and create ionization that way. There's also energetic particles from the magnetosphere that come in, and they also create collisions and create ions in the lower atmosphere. And then finally, at the surface, you have radioactive decay when outcome is radon. And that radon will come up and emanate from the surface and create charged particles. So the distribution from the surface all the way to the edge of space is variable, but it's this distribution that is so challenging because there's chemistry and there's physical pathways and there's external sources and forces that make it very difficult for us to account for it all. But we know those ions constitute the conductivity of the atmosphere.
And this is not something that a lot of people know, but by the end of this talk, you will also be experts on this. So the reason that we are interested in these clouds is they become charged, and that charge can influence the cloud microphysical processes inside the clouds, and that may have potential implications for climate. So I'm going to talk you through all that tonight. So we will start off discussing how these clouds become charged, how we know they're charged, and that's through some measurements that we've made with bespoke balloon instrumentation that we've developed at Reading. I'll then discuss what the effect the charge has on the droplet behavior. And then I'll talk about some novel experiments that we've been doing in fogs to demonstrate or to try and find some evidence whether charge affects cloud properties in the real environment. And then finally, I'll discuss what the implications of this are for weather and climate, because this is very much an understudied effect. It's not included in climate models, and it's not widely studied. So there's lots to learn about it. So we'll start off discussing where the charge comes from, basically. So if you forget everything else I say tonight, the one thing to remember here is that Earth's atmosphere is always electrified. Normally, we just think about charge when there's thunderstorms and lightning around, but it's electrified all the time, and charge is continuously generated. And that's through a process called ionization. So positive and negative charge is created by ionization all the time. And in our atmosphere, there are two sources of ionization. The first is from galactic cosmic rays. So these are highly energetic particles from basically outer space, from outside our solar system, and they enter Earth's atmosphere from above. And as they do so, they create a cascade of charged particles right down to the surface. And because they come from outside our solar system, they're modulated by solar activity. So they respond to magnetic fields. The other source of ionization is radioactivity at the Earth's surface. So this is mostly from gamma radiation from the soil. And so this emits ions which can be transported upwards, but they're typically trapped in the boundary layer. So they're stuck in the lowest kilometer of the atmosphere. So this charge is being generated all the time. And initially the charge exists in the form of really tiny nanometer-sized charged ions. But they don't stay tiny for long because they interact with atmospheric molecules and aerosol particles and droplets. And this is the subject of a totally different talk, or 3 totally different talks, but I just wanted to make you aware that charge can actually affect many different types of aerosol and droplet processes. Some of the things that we've studied, for instance, is the charge effect on long-range dust and volcanic ash transport. So the idea here is that the charge can maintain the dust or the ash in the atmosphere for longer than it would be normally. And this might explain some strange observations of large dust particles that are transported huge distances and nobody can explain why. Another thing that charge might affect is the radiative properties of dust layers. So there's been some theory and measurements that suggest that the particles can align in the electric field and act like a Venetian blind type effect, which affects the amount of solar radiation that's transferred through a dust layer. And then the other thing, which is what we're going to talk about tonight, is the effect of charge on cloud microphysics. So another concept that's important here and that's related to charge in the atmosphere is something called the Earth's global atmospheric electric circuit. So I should probably move this because you can't actually read the title of these slides. So the global circuit, not much better, is it? It's okay, it's fine, good point, it disappeared, sorry. So the global circuit is a hypothetical concept which describes current flow around the planet, basically. Why are we not moving? There we are. Okay, so this was suggested by the Scottish physicist C.T.R. Wilson in the 1920s. So this is the same C.T.R. Wilson who invented the cloud chamber, but he also worked in atmospheric electricity. And in this circuit, we have Earth's surface and the ionosphere, which is a layer in the atmosphere about 60 kilometers up. And these are highly conducting regions. And the idea is that we treat these two surfaces as the plates of a spherical capacitor. And in the middle, we have the atmosphere, which is weakly conducting because of the ionization from the cosmic rays and the radon. And this charge that we have, this positive and negative charge, becomes separated in thunderstorms. So the top of thunderstorms become positively charged and the bottom become negatively charged. And this charge is transferred up into the ionosphere and the negative charge is transferred down to their surface. This creates a huge voltage difference or potential difference between these two plates of the capacitor, which we call the ionospheric potential. And it's about 200,000 volts. So if you were to connect a wire between the ionosphere and the Earth's surface, there'd be a 200,000 volt difference, which is enormous. And that voltage difference, and because we've got charge carriers, means that we have a tiny little current which flows, which we call the air-earth conduction current, or JC. And it flows everywhere. So it's not just related to thunderstorms. It flows in all fair weather regions of the atmosphere. It's flowing right now. So the two things that you've got to remember as we go through this talk, the two concepts are this vertical conduction current, JC, and also the concept of an electric field. So this global circuit sets up an electric field in Earth's atmosphere, which again is everywhere. And near the surface, it's about 100 volts per meter. So that means there's about 100 volts between my feet and about here. We also call it the potential gradient. So I'll use electric field and potential gradient sort of interchangeably in this talk, but they basically mean the same things. It's just one's the negative of the other. So we've got a conduction current density and we've got an electric field set up by this global circuit.
This is the Endurance rocket ship, and she's about to discover something incredible and fundamental about the Earth. So why here? What makes Earth this special place that we all call home? One of the reasons may be due to the energy fields that our planet creates. So the first one's gravity. You're very familiar with gravity. It's important for life because it's holding our atmosphere on. If you don't have enough gravity, your atmosphere tends to escape to space, like at Mars. The second field is the magnetic field. It's this shield that's protecting our planet from the stream of particles that comes from the sun. So our rocket has discovered and finally measured number 3. It's called the ambipolar field, and it's an agent of chaos. It counters gravity and it strips particles off into space. Whenever spacecraft have flown over the poles of the Earth, they felt this supersonic wind of particles called the polar wind, flowing out into space. There must be some invisible force lurking there responsible for this outflow. But we've never been able to measure this before because we haven't had the technology. So we built the Endurance rocket ship to go looking for this great invisible force, right? This ambipolar electrical field for the first time. So we were expecting to hopefully find the source of this polar wind, but what we weren't expecting was this other thing that it does to our skies and to the atmosphere, which is just so profound. There's only one launch site in the world far enough north to actually try and launch into this thing, and it's in the very north of this tiny island called Svalbard, just off the coast of the north of Norway, which meant a little bit of a trek to get it to the launch site. About to sail today from Longyearbyen to Ny-Ålesund, up the coast for about 14 hours. We had a couple of days of being completely whited out, and now it's calm in this beautiful country. I have a feeling this might be the day.
Solar.
Solar go.
Radar.
Go.
Mission control, this is Endurance. Go flight. We are go for launch.
Yep, check 146.
I think we're about to launch a rocket.
3, 2, 1! Ignition! Knocking down!
During the 15-minute suborbital flight, we successfully measured this ambipolar field for the first time. When you add up all of the strength of it over the whole flight, the whole potential drop was only about half a volt. And that's nothing, right? That's about as strong as one of those tiny little watch batteries. But that's exactly the amount that you need to explain this, polar wind escape, this outflow. Because we measured it for the first time, we can actually understand the role it plays in the atmosphere. And despite being weak, it's incredibly important. It counters gravity and it basically lifts the skies up. It's like this conveyor belt that's lifting this atmosphere up into space. So like us, you're probably left with a lot of questions, right? What does this field do? What's it for, right? How does it shape the planet? And I can't tell you yet. This field is so fundamental to understanding the way the planet works. And it's been here since the beginning, alongside gravity and magnetism. It's been lofting particles to space and, stretching up the skies since the beginning. It's probably had an impact on the evolution of the atmosphere, but I can't tell you how much yet. It may even have left a mark on the oceans, but how much I don't know. This field is a fundamental part of the way Earth works. And now we've finally measured it, we can actually start to ask some of these bigger and exciting questions.